Hello everyone, I am Avirup Mandal. Today I am going to present our work on interactive physics-based virtual sculpting with haptic feedback. This work has been done in collaboration with Professor Parag Chaudhuri and Professor Subhasis Chaudhuri. All three authors are from Indian Institute of Technology, Bombay. Real-world sculpting relies on visual as well as tactile feedback. However, the traditional virtual sculpting tools like ZBrush, Blender, etc. does not render the tactile part of the feedback. So in this work, we propose to make the virtual sculpting experience more accurate and immersive by adding haptic feedback and physics-based sculpting. Our goal is to build a virtual sculpting solution with visual as well as haptic feedback. For that purpose, we developed a remeshing-free, improved stable extended finite element method based cutting algorithm. Here you can see in the video on the right side of the slide, first using a cutting tool, we cut the object mesh. We synchronize haptic and visual feedback using a multi-resolution, multi-timescale method to run the whole system faster. And finally, we make part of the simulation parallelized using GPU to meet the real-time constraint. Along with the cutting, we have used a wetting brush to wet part of the object to make the object more malleable, and then use a deformation tool to deform the object. The wetting and the deformation part of the sculpting has been taken from one of our previous work. Among the existing remeshing-free cutting algorithms, XCFM algorithms are most popular. They add extra degrees of freedom to the cut nodes using an enrichment function. Because of this enrichment, the disjoint pieces can move independently without any explicit remeshing. Improved stable XCFM-based algorithms are more stable version of XCFM. Using a linear interpolant, IXXFM reduces the condition number of the system matrix, thus rendering the system more stable. There are two popular ways to render haptic feedback for solids. One is constraint-based haptic rendering. Here the haptic proxy goes inside the object mesh, but the God object, which is the replica of the haptic proxy, is constrained to stay on the surface of the object mesh. And the difference between the acceleration of God object and haptic proxy is used to calculate the haptic force feedback. The second major method is penalty based haptic rendering. Here the haptic proxy goes inside the object mesh, and depending on the depth of penetration, the haptic force feedback is rendered. In our work, we have used IXFM and penalty based haptic rendering for our work. Among the existing virtual sculpting algorithms, cube grid based field sculpting use small cube grid voxels to model volumetric mesh. Displacement maps has been used to manipulate 2D surfaces. B-spline is also used to deform 2D surfaces which is embedded in a 3D mesh. We have noticed that high resolution mesh slows down the simulation speed. This in terms make the haptic feedback discontinuous and jerky. On the other hand, low resolution mesh affects visual fidelity. So to meet these two disparate demands, we embed a high resolution triangular surface mesh for visualization inside a low resolution tetrahedral volumetric mesh, as shown in the figure here on the right side. Now, sculpting operations are first performed on the low resolution volumetric mesh. After that, these sculpting operations are transferred to the high resolution mesh using a barycentric coordinate system. To render smooth haptic force feedback, we use continuous collision detection between the cutting tool and outer surface of the mesh being sculpted. In continuous collision detection, each time step has been normalized between 0 to 1, and between the 0 to 1 we find out where the two objects, that is the cutting tool and the outer surface of the mesh, is getting collided. For example, here in the figure, at t is equal to t dash, the collision starts, it goes up to t equal to t double dash. Again at t equal to t triple dash, it again starts colliding and it goes up to t equal to 1. So here you can see t is equal to 0 to t equal to t dash and t equal to t double dash to t equal to t triple dash. Between these two intervals there is no collision. Along with the continuous collision detection, smooth haptic feedback requires 100 frames per second update rate. However, the visual feedback requires only 60 frames per second. For this purpose, we have rendered our whole simulation in two different parallel threads. One is haptics and the second one is visual. The haptic thread has been kept running at 1000 frames per second, whereas the visual thread runs at 95 to 150 frames per second depending on which kind of mesh we are using. Now, in visual thread we perform all kinds of physics based operation. Thus the force update happens in visual thread. The haptic thread gets this updated force by using a rapid update method, and we also use a shared memory to transfer the data between these two threads. For haptic feedback, we have rendered two different kinds of force feedback. First one is vertex face penalty force. In this case, the vertices of the cutting tool is been collided with the triangular elements of the outer surface of the mesh getting sculpted. Now, in the figure you can see this node and the triangular surface. The formula for this vertex force penalty force has been given here as shown. Pt is the position of the vertex P at time t, Qt is the collision point at time t, and Nt is the normal of the triangular element at time t. This t equal to Tia and Tib denotes the timing interval at what time this collision is happening. Kvf is a user defined parameters. Similarly, we calculate the edge penalty force where the edges of the cutting tool is getting collided with the edges of the sculpted mesh. Here the formula is exactly same except the Ke, which is another user defined parameters. For physics based cutting simulation, we use improved stable extended finite element method based algorithm. In this method, first we find closed loop intersection of the cut tool and the tetrahedral element. Here the cut tool has been shown using this green colored plane. Now when the cut tool is penetrating this object mesh, haptic force feedback gets generated. When this haptic force exceeds the critical threshold, we mark the overlapping portion between the cut tool and the tetrahedral element as cut. So here you can see this closed loop cut intersection using this red dotted line. Once this cut is done, we enrich the corresponding nodes. Enrichment denotes the extra degrees of freedom. So here the 4 enriched node for the tetrahedral element is shown with this red circle. The enrichment function has been denoted using this formula here. Here ui denotes the displacement function for node I when there is no cut is present. Uij denotes the displacement function of node I for cut j. Ni is the linear shape function. Psi ij denotes the enrichment function for node I for cut j. The enrichment function can be denoted as shown here. Hs is Heaviside function, k is a user defined parameters, and gamma is a linear interpolant which is defined as here. Now the difference between the IXFEM and XCFEM is that if we make k is equal to 0, this enrichment function will resemble a XCFEM enrichment function. Because of this use of linear interpolant function, the condition number of the system matrix gets decreased for IXFEM, which makes the system more stable compared to XCFEM. For any tetrahedron E which has j number of cuts, using this enrichment function as defined in the previous slide, we rewrite the mass function as shown here. Similarly, we can rewrite the external force function using this formula here and internal force function using this formula here. Now please note, because of the discontinuous nature of the enrichment function, all these enriched mass, external force and internal force integrals are discontinuous. Now to integrate these kinds of discontinuous integrals, we used a Gaussian quadrature method. In this method, if a cell K is cut by a plane, here the plane is shown in red circle, let's say we have got the subdomain A. We have to integrate the volumetric integrals on the subdomain A. However, directly integrating this volumetric integral is very difficult. So first we transfer these volumetric integrals on the surfaces as surface integrals. So here by this we mean these volumetric integrals of subdomain A will be transferred on the cut interface I and the bounding surfaces of K. Now directly integrating this surface integral is also very difficult. So we transferred this surface integral to line integrals. For example, for this top surface here, we see that these three lines and the bounding lines of the cut surface should be integrated. Once we get the results from these line integrals, using that we can get the results of the surface integrals, and from there we can get the volume integrals. More details about this Gaussian quadrature method has been given in our paper. Now we present some of the results using our framework here. First, you can see a high resolution volumetric mesh has been embedded in a low resolution cage mesh. As the cage mesh moves, the visualization mesh also moves. Here we show the results of cutting the object mesh. First we mark a cut at the back of the object, and then we mark a cut at the front of the object. Finally, we let the object sag under gravity, and you can see the cut openings here also. Here we perform all three operations. First we mark cutting on the object mesh, then we weight part of the object mesh, and finally we weight that portion of the object mesh using a deformation tool. Here you can see that user is making part of the object weight by transferring water from the weighting brush to the object mesh. Then he is using a deformation tool to deform this object mesh. Here we show the results of a sculpted object using our framework. To evaluate our framework, we have performed two different kinds of user study. The first one is ANOVA study to evaluate the effect of haptic feedback in virtual sculpting. So here you can see our system framework where the user is manipulating an object using a handheld haptic device. So here we have designed three different kinds of strategy. The user is asked to perform this sculpting operation when both the visual and haptic feedback are on. As a second strategy, when the visual feedback is on but the haptic feedback is off. In third strategy, when the visual feedback is off and the haptic feedback is on. By visual feedback off, does not mean that we do not render anything on the virtual screen. Here we mean that the sculpting operation that is being performed on the mesh will not be rendered and the original mesh will remain intact. So our null hypothesis is that haptic feedback does not improve the user experience during virtual sculpting. However, from the compared strategies p-values and the mean median parameters, we can understand the haptic feedback improves the user experience during virtual sculpting. However, when the visual feedback is off, the user experience degrades significantly, which is intuitive because our eye is the most dominant sensory among all the other six senses. We performed another study called double seamless comparison study to compare our math method with real world physical sculpting. In this method, the user are first asked to perform sculpting using a ball of clay with their hands and a knife and tools. Then they are asked to perform our sculpting using our virtual sculpting framework, and finally rate our virtual sculpting framework on the three parameters here. First one is realism, how real their virtual sculpting experience is compared to the real world sculpting. Second one is visual haptic synchronization, whether they experience any kind of delay between the haptic and visual feedback. Third one is physical consistency, how our overall system is compared to a real world sculpting framework. Now from the ratings the user has given, we can conclude that our framework closely imitates the real world sculpting experience. To conclude, we built a physics-based virtual sculpting framework for soft deformable objects with real-time accurate haptic feedback. One of the drawbacks of our framework is that the system size, matrix size of IXFFEM increases with increasing number of cards. we would like to develop a solution whose runtime is independent of the number of cuts. Thank you for listening. I will be happy to take any questions that you have.